Hi, do you like math? Of course you don't. You look at this and think this is fun. No one does. I have an undergraduate degree in applied math with specialization in image denoising, noise minimization, image processing, and analysis. Ooh. Okay, so I thought maybe I could take some of this and turn it into math. That is fun. You know why? Because math doesn't have to be bad. You can look at this and you go, this is terrifying. Or you can start out simple. How do you start out simple? With numbers. 1, 2, 3, 4, and so on. Eventually you get to infinity. That's not a number. That's a concept. We love it. We love you, infinity. Anyways, so what are all these numbers? Let's define them. Let's define numbers in two ways. Even numbers and odd numbers. We all know what those are. Even numbers, 2, 4, 6, 8, 10. Odd numbers, 1, 3, 5, 7, 9. Seems pretty simple. Seems pretty reasonable. But how do you define those? They all have their own special definition. Well, the even number we can define in this way. 2n, where n is what? N is an integer. What's an integer? An integer is basic numbers you know, from everything from negative 15 to negative 100 to positive 100 to positive 2, 7. Anyways, so we take any number, any integer like that, multiply by 2. Let's try it. 1 times 2, what does that equal? That's 2, that's even. 3 times 2, what does that equal? That's 6, that's even. 112 times 2, what does that get? 224. Guess what that is? Even. Okay, so let's firstly divide, talk about the odd numbers. Let's define the odd numbers. What are the odd numbers? Well, we define the even numbers as 2n, so let's define the odd numbers as 1 different. 2n plus 1. Again, n is those integers. 117. So we choose anything. Let's choose 3 again. 2 times 3 plus 1, 6 plus 1, 7. That's an odd number. 2, 14 plus 1. 28 plus 1 is 29. Odd number. So you see what I'm getting at. Okay, but let's start grouping these numbers together. Say we look at the even numbers and the odd numbers. We already looked at a group of numbers. We called them integers. Those were our regular old numbers. Then we have the natural numbers. Those are our counting numbers. That's specifically 0, 1, 2, 3, ... We start at 0 here. That's the important part because we count with them. You don't count with -1, you count with 0. Sometimes. But you count with 1, 2, 3, 4, Okay, but we also have something else. We have the rational numbers. Now, what's a rational number? Rational numbers, what we know. We have some regular numbers. We have 1, 3, 118. We also have 2/3. We also have 5/3. We also have 3/4. We also have 17 18ths. Okay, these are rational numbers. Specifically, we're saying if we take a rational number, we can divide it as n over m. What is n and what is m? They're both integers. So we've taken integers and we use that to define rational numbers. However, there's an important piece to this. M cannot equal 0. You know why? Because if you get n divided by a 0, that is bad. See that? You know what happens? The universe ends. So yeah, we don't want to do that unless you're a supervillain, which I might be, but not disclosed until later. So we continue on. Now we've looked at the rationals. The rationals are regular stuff, but what about real numbers? We just want to say what's a general real number we can think of. That's anything we can think of. So we can think of our rationals. That's 2/3 again. That's 4/6. Guess what? That's also 2/3. That's 9/9, which is just 1. That's again 17, but this time over 19. But it's also something like pi, the square root of pi, square root of 2. 7. Most of these seem simple. Most of these fall into the area of n over m, number over number, except these 3 certainly do not. They fall into examples like 3.14, but it actually goes on for a while. 1.77, but it actually goes on for a while. This is also like 1.7-ish. Goes on for a while. Let's double check that. 2 root was 1.4. Anyways, see, it's a confusing one. Now, what does any of that mean? That gives us real numbers. These are numbers that exist, that we can work with. We work with pi all the time. What's the area of a circle? Area equals 2 pi r. Just kidding, that's our circumference, but our area is pi r squared. So then we can work with pi, we can work with irrational numbers, and guess what? We can know what the area of a circle is, and it's not crazy. It's consistent. That's math. But guess what? Math doesn't have to be scary like that. Math can be simple. Let's start by continuing. That didn't make a whole lot of sense, now did it? Anyways, so we're looking at the real numbers. If we look at the real numbers and we look at the rational numbers, the real numbers is a bunch of stuff and the rational numbers is a bunch of stuff. We'll say, what about the real numbers, but without the rational numbers? That gets our irrational numbers. That's going to be everything that's in the real numbers. So it's n in the real numbers such that n is not rational. Okay, we have to find a whole bunch of stuff. What if we wanted to find the entirety of the real numbers now? What are you going to say? The irrational numbers combined, that's the wrong one, combined, unioned with the rational numbers. So that's all of our crazy stuff. That's our square root of pi over 17. And this is 17. And then you're combining all of them, and that will get us real numbers. That's just all of our usual numbers. There's also imaginary numbers, complex numbers. Those have i's. That I is the square root of -1. We don't have to worry about that right now. Why? Because that doesn't come into play for quite a while until you get into a complex field. And you don't get into a complex field until you're dealing with some more complex stuff. Surprise, surprise. Wonder why they named it that. Anyways, so you have all these real numbers, but now let's think about something else. Let's think about the rationals. Let's think about the rationals intersected with the integers. What do you get? Well, if we know that every single integer or every single rational number can be defined as n over m, and we think about every integer is just a regular n or m, well, guess what? N and m are n over 1 and m over 1, so that's inside of that. So we know that z is a subset of the rationals, but all of the rationals n over m, if that's 2/3, 2/3 is not an integer. Therefore, we can say that our intersection here is in fact just z. We've intersected. It's all a little piece of it. All right, that gives us a good baseline to go off of. That's a good starting point. You looked at sets, you looked at numbers, you looked at tons of stuff, and guess what? You don't have to look at all this just yet, but all this will come in due time. What do we have? We have a Maclaurin series. We have a shell method. We have probability in high dimensions. We have determinants. We have inverse. We have composite functions. We have supremum and phenum. We have metric spaces and triangle inequalities and differential equations, and that's all scary, but guess what? It starts with even and odd. So anyways, I've been Kronk. I say hey, and now I say bye-bye.